in Cohere's LLM. Everything from thinking about what pre-training data we're going to use all the way up through evaluations and more. Before I joined Cohere, I did my PhD at Johns Hopkins University in multilingual NLP. Okay, so today I'm going to be talking about our recent preprint called How Does Quantization Affect Multilingual LLMs? This was done as a collaboration between a handful of researchers at Cohere and at Cohere for AI. So the outline of what we'll talk about today, I'll talk a little bit about the background and motivation for the problem. We'll talk about the experimental setup. We'll discuss the results. If you have any questions throughout the entire presentation, it should not be the whole hour, so feel free to interrupt me and we can keep it casual and chat during the talk also. Okay, so to reach the world, multilingual LLMs need to be highly performant and also lightweight. So there's a paper that came out in 2021 where they coined this term called the low resource double bind. And that's the fact that often where you see the need to cover more languages are also coincide with the places that you need the LLMs to be more performant, because maybe you need them to run on lower cost hardware. So quantization is one way that people try to reduce cost for LLMs. They improve inference speed. Quantization also can enable wider deployment because it allows you to serve LLMs on lower cost hardware and hardware that's more available to your average person. But quantization can definitely affect downstream performance. So we wanted to know, how does it affect performance for multilingual LLMs specifically? There's a huge literature that talks about how quantization affects performance in general, but it almost exclusively focuses on English. So we were the first work that we are aware of that has looked at quantization in a broad variety of multilingual contexts. Okay, so what is quantization? Quantization compresses the weights and potentially the activations of a neural network to lower bit representations. You can do this quantization either by training the model itself at a lower precision, and this is called quantization aware training, or you can train the model at a higher precision and then quantize the final model weights before you serve them. And this is known as post-training quantization. Post-training quantization is simple, it's easier, and you can apply it at scale. So in this paper, we focused on PTQ. Okay, so one way to do quantization is called weight-only quantization. So this is where you're going to quantize only the weights of the neural network to get them into a lower bit representation. So these are quantized offline, and then the compressed matrices are loaded from memory into the tensor core during inference. This way you can have a smaller memory footprint, and also if you are in a memory-bound scenario, you can do faster inference if you do weight-only quantization, because there's simply just less bytes to transfer from memory to the compute units. So we have the equations for how you do a very simple form of naive weight-only quantization. Basically, this is actually quite simple. You're basically just going to take the maximum value that you find in the weight matrix, the maximum absolute value. You're going to divide it by the bit precision that you want. So if you want 8-bit precision, and it's going to equal, well, this 2n minus 1 is going to equal 127, because that's the maximum span of values that you can get with 8-bit precision. And then you simply divide your weight matrix by that scaling factor that you found. Delta is called the scaling factor, and you round every value to the nearest integer. So this is the simplest way that you can do quantization. You can also do weight and activation quantization. This quantizes model activations alongside with the weights. Unlike weight-only quantization, quantization of activations happens at runtime. So you're going to have to calculate the quantization scaling factor dynamically for each input on the fly. And this, as with the quantization that affects the precision of the weights, this is of course going to affect the precision of the activations and increase the error a little bit, but it allows you to use more specialized low precision hardware that's available for in modern GPUs. And then we have the equations for this. The reason these look a little bit different is because before we did a very naive one scaling factor for the entire matrix just to show you in the equation. And this one, this is per column. So it's just a little bit more granular, but you're still going to get quantization of the weights and then quantization of the activations. Okay, smooth quant is a method that was created to ameliorate the issue of activations being difficult to quantize due to peakiness. So usually when you have a matrix, a lot of the values in the matrix, in the weight matrix, are going to be pretty close in value, pretty not have a lot of outliers, but it turns out that on the activations themselves, you tend to get more outliers, which if you're quantizing based on the value in the matrix with the highest absolute value, if you have outliers, and that really severely affects the scaling factor. So smooth quant was created as a way to shift some of the burden of these peaky activations onto the weights, therefore making the weights a little bit harder to quantize because now they're a little bit peakier, but the activations are a little bit easier to quantize. And it turns out that often in practice, if you do this smooth quant, you do get a little bit better performance downstream. And it's done in a mathematically equivalent way to not applying smooth quant, but it just tends to improve performance, at least on English. We'll see for us, spoiler, that sometimes it's going to help, sometimes it's not, but that's for the results section. Okay, so for our experimental setup, we evaluated 4 models in 2 main families of models. So we have the Command R and R Plus series, which you all must know is the proprietary models from Cohere. They come in sizes 35B and 103B. We also quantized IA 23 and IA 101. Sorry, actually, I should correct this. I think we only did IA, I'll have to check the paper, but I think we only did IA 101 in this, but we did it at the 8B size and at the 30B size. We evaluated these models under W8, W8A8, W8A8 with smooth quant, W4G and W4. So the way that you understand these, weight only quantization is going to be called W something. We have an implicit A16 activation stay in FP16. So W8 up here, if you wrote W8A16, that would be equivalent. W8A8 takes the weight matrices to 8-bit and also the activations to 8-bit. This is the same, but applying the smooth quant that I mentioned. W4, this would be the same as W4A16. W4 takes the weight matrices from FP16 to int4. And then this is a special, better way of doing quantization that we'll see comes out in our results as being better, but it's still W4 weight only quantization, but they just do it in a smarter way. Okay, so we evaluated on all of these languages belonging to various different language families and using various scripts. We are mostly going to look at relative degradation versus FP16. So as opposed to reporting raw scores, which we do in the appendix of the paper, what is really important to help us understand what happens is to compare the scores when the model was in FP16 versus when it's in its quantized variant. So the metrics that we report through the main body of the paper are, we take the score that was received from the quantized model, we subtract the score from the FP16 model, divide by the FP16, so you get the ratio of what happened when you did the quantization. Yeah, then you multiply by 100, of course, to get the percent delta, which is the percent typically degradation. You will see in the results, sometimes you get a little bit of a performance boost actually from quantization on some metrics. Still not 100% clear whether that is noise or a real signal, although we have seen in some literature that in some cases, a bit of noise introduced through things like quantization or compression might be helpful, but that is still a speculative statement that I've just made and needs a lot more research. Okay, so we have a variety of automatic benchmarks that we'll run. The first is multilingual MMLU. Here's an example. So they are questions from people probably know this, but there are questions from a variety of topics. You get an A, B, C, D answer choice, and then the model has to predict whether the answer is A, B, C, or D. So this is in question answering. There is a public copy version by the University of Oregon that you can find for a variety of languages. When we evaluated Command R, we weren't entirely satisfied with that version because it was translated with ChatGPT. So we actually use our own translations that we did with Google Translate. If you do look at the paper, in the talk, I'm basically just going to talk about the Command R results because the IO ones were very similar, but there are subtle differences in the test sets between the two. For instance, in the Aya eval, we wanted to keep consistent with what Aya had evaled on in the past, so we did use the OCopy version for that. But again, side note, and the Aya results are all in the paper. We have MGSM, so this is Multilingual Grade School Math. If you're familiar with GSM 8K, this is essentially that test set. It's a sub-selection, but then human translated into a variety of languages. So here you get relatively simple math word problems. We then ask the model to provide a step-by-step answer, and you get an accuracy over that test set. We also have Flores 200, which is a widely used translation set from Meta. In this example, everything, the English side of each of these test sets is exactly the same. So whether we're looking at English to Vietnamese or English to Russian, we have the same semantic information contained in those translations, which is kind of nice. So here you might see translate from English to Vietnamese. We ask the model to output only the translation because some LLMs tend to be chatty. We give the English sentence, and then we ask for the translation. We also eval on what is called a language confusion benchmark. If you have not seen this, this is because this is very new. This was another Cohere paper from about the same time that this quantization paper was released. They were worked on simultaneously. But basically the idea here is that LLMs have a hard time in certain scenarios maintaining the ability to create text, to produce text that's not in English. So you might have seen this before. If you try to prompt, say, ChatGPT or command in a non-English language, especially if the domain is a bit esoteric, you might get full sentences and output in English. The whole response might be output in English. A little bit less severely, you might have single words that appear in other languages, like in English. And this is a problem that we see in all of the mainstream LLMs. We've been trying to correct this at Cohere, but we also wanted to actually measure it because no one to date had measured this. So we developed the language confusion benchmark. You can find that paper on arXiv, but essentially what happens here is there are a couple settings. In one setting called the cross-lingual setting, we will have an English prompt, and then we'll say something like reply in Japanese. Might on the surface look artificial because usually you'd expect, oh, a Japanese user will type in Japanese, and I think that is true for your average user, and we do have that setting in the paper, which we call monolingual. So the prompt will be in Japanese, you expect the output in Japanese, but it turns out that in business use cases, you often do see scenarios where you have prompts in English, but then the downstream user is going to be using it in a different language. So you actually do have these embedded reply in Japanese or reply in Korean or something. So in this paper, for simplicity's sake, we only used what we call these cross-lingual prompts. So it's English prompt asking for the response in a non-English language. The metric that's used in language confusion is line pass rate and word pass rate. I don't have slides on that, actually. I should have put that in here. But basically, line pass rate, if you prompt a model and any sentence or any line is in the wrong language, then the model fails on that example. So it's an all or nothing metric. Either you get 100% of lines correct, or you have one mistake and you get a failure. So we calculate a pass rate over that. So that'll be how many responses out of 100 had no line level errors. The reason that we are so strict with that all or none is because at first we used accuracy, but really if you are a user of an LLM, if you're going to be practical about these things, as Cohere tries to be. If you're a user and you get even a single sentence that's not in a language that you know how to understand, it's a really bad user experience. So, you know, I'd say if 1 out of 4 lines comes out in English and you don't read English, you don't like the response 75%, you basically probably don't like the response at all because you couldn't read part of it. So that's why it's an all or none. Word pass rate is the same, but it's even more strict. So on this one, if the entire model response is in the right language, you get a score of 1. If any single word in the entire response comes out in the wrong language, you get a score of 0. And we calculate a pass rate over that. Okay, we also have LLM-as-a-Judge, RM-as-a-Judge, and human evaluation benchmarks. For cost reasons, of course, we could only do this in a handful of languages. So we produce the model outputs for French, Spanish, Korean, and Japanese. In human eval, we did have annotators that looked at all the responses. And then we did LLM and RM-as-a-Judge over 2 evaluation suites. The first one is an internal Cohere evaluation suite with 150 diverse prompts. And these are designed to be pretty challenging, more complex than public evaluation benchmarks, because we found that in the public benchmarks, LLMs have gotten good enough where a lot of these are really easy and you don't get a lot of signal to be able to differentiate models when you're evaluating on easy prompts. These were translated from humans, or by humans, from an English seed prompt. So that means that all 150 prompts for all of these languages contain the same semantic information because they were all seeded with the same prompt from English and then human translated. We also have the Aya DALI 200. So those of you that have been involved with Aya will recognize this. The Aya project released a handful of data sets and we use some of theirs for evaluation here. So for Korean and Japanese, there were automatically translated questions from the DALI 15K set, and then these were human curated to maintain their quality. For French and Spanish, these are from the DALI human edited set and a post-edited version from DALI machine translated. So you can refer to the Aya papers to understand those. But in general, I'd say that when we look at the results, we'll keep in mind that this internal evaluation suite is meant to be more challenging, and the Aya DALI 100 is a little bit more simple prompts. Okay, do we have any questions before I go on to the results? Because I'm kind of flying by things right now.
I was curious, like right at the start, typically the idea of quantization aware training kind of would be to inject some noise, so PTQ is better in that sense. Like, so would you be doing both in some sense in these ideas?
So in our work, we only quantize after training, and that was for simplicity and also because we expect that for your typical user, they pull a model off Hugging Face, they quantize it, and they use it. We didn't get into quantization aware training at all.
Okay.
But yeah, so honestly, as an extension work, it would be great if someone ran those experiments.
Yep.
Yeah. Okay, we have another question.
Yeah. Hi. Hi, Kelly. So
Hello.
basically, during the dataset evaluation, what kind of heuristics do you mainly watch for in respect to, I guess you guys use SP Blue and Rogel?
Right. So when we get into the results, I will show you the metrics. For Flores, we used SP Blue is what we reported. Ideally, one would use something like Comet nowadays.
Oh, okay.
Yeah. So yeah, were I to extend this project, it was done, you know, on a condensed time frame. But were I to extend this, I think the feedback that I would get from MT researchers is to also include a metric like Comet.
Okay. In particular to the translation, am I right?
Yeah, for translation. And then for the other ones, for MMLU, this is just accuracy over the test set. I will show you the aggregate values for the entire MMLU test set, which is about 14,000 questions. There are categories in MMLU. I did the breakdown by categories. You know, some is STEM, there's various categories. And I actually expected that I would see a difference between the category types in the performance, and I did not see that. So in the paper, I ended up just reporting the aggregate. MGSM on math is also just an accuracy. How many questions do you get correct? And language confusion is this pass rate. So like each model response gets a 1 or a 0, and we calculate how many responses got a 1 out of the entire test set.
Okay. Yeah, I guess that's clear. Thank you.
Yep. Any other questions?
I think I had 2, 3 more, but I could go after the results because they're also related to that. So
okay, yeah, sounds good. Okay, so let's get into the results. And yeah, we're good on timing, so I have plenty of time for questions. All right. Okay, so what did we find? First, and potentially most importantly, we found that automatic metrics severely underestimate damage done from quantization. So if you read a majority of quantization papers, a lot of them will allege no degradation from the baseline, but a lot of them will only have run on automated metrics. So our evidence is that that really hides the damage that's done here. So for instance, in this chart, I just showed results from French and Japanese. In the paper, it's got everything else. But if we average over all automated metrics for a 103B W4 quantized command model, we only see 0.3% degradation on French, 1.7 on Japanese. But in human evaluation for both of these, we've dropped at least 16 percentage points or higher. And for certain tasks this would have probably been even worse. So while automatic evals estimate deterioration of a quantized model relative to FP16 across tasks at a modest, the modest percentages that I said, humans report the drops as much, much worse, which shows how important it is to actually get real humans to look at your outputs. Then we had the hunch that potentially languages might be treated disparately by quantization. So we thought that potentially Latin script and Indo-European languages would be hurt less than languages that use non-Latin scripts or non-Indo-European. And we found that that was true. So if we look across the x-axis, this is in order of increasing quantization. So W8 is the lowest quantization that we have. Latin script and non-Latin script are treated basically the same in automatic metrics. But as we increase the quantization, we see this gets even worse, where the gap between the Latin script Indo-European languages and the and all the other languages gets even wider. So we already knew that non-Latin script languages are poorly represented in training data and tokenization. We already knew that they often had worse performance overall. They're a little bit neglected. And because of the increased fertility in the tokenizer, they often actually cause their users to have higher cost and latency. But now we know that they're also unfairly treated in quantization. So we really need more focus on these. Yes, do we have a question?
Hi, Kelly. Just a quick one there. Are Indo-European languages represented better? Is that why you thought they would be better?
Yes. So on the command model, the overlap between Latin script and Indo-European was 100%. And that's not always true because there are Indo-European languages that don't use the Latin script. But yes, this is our hypothesis. Someone should test this. But the reason why I thought this would be true is because models tend to be English-centric. So you're getting a lot of training data. Those tokens are going to be well represented. They're well represented in tokenizer training. They're well represented in model training. And also, even if, say you have a Latin script language like Galician or something, even if you're not seeing a lot of Galician data, it's still using the same characters as other languages that we see a lot,
right,
which are being well trained. So my hypothesis here is it has to do with under-trained tokens in non-Latin scripts.
Makes sense. Thank you.
Yes, but if anybody would like to extend the work and test that hypothesis, that would be great. Okay. We also found that challenging tasks degrade the fastest. So it's difficult to decide what is a challenging task and what is not. But we typically thought that tasks like mathematics would be harder than a lot of the other ones. For instance, MMLU, multiple choice is still hard, but you still only have 4 choices. MGSM, this actually has to generatively produce the answer to a mathematical problem. So there's a lot more that can go wrong here. LLM-as-a-Judge, this was answering, the model wasn't answering actual prompts and the LLM was judging it. So we found that challenging tasks do seem to degrade the fastest. This is for a 103B W4 quantized command model. Human eval, the reason why this is starred is because we only did human eval on the W4G variant. So W4 with group-wise scaling. That's because it's just a better way of doing W4 quantization. We had limited human eval resources, so we didn't have the resources to eval both of these. My guess is that if we had human evaled the naive W4, this would be considerably worse. But even with W4G, a 10% degradation is not what you want. So yeah, MGSM and generative tasks evaluated by humans and LLM-as-a-Judge suffer a large performance penalty under quantization. So I talked about 2 methods that you can use instead of naive, say W4 or W8A8 quantization. The first was smooth quant. Again, as a reminder, that's where we take some of the burden of the peaky activations and we shift it to the weights to make it easier to quantize. And yeah, for W4G, I'll refer you to the paper, but basically it's just a smarter way of doing weight-only quantization. So we wanted to see, do those methods actually help us? So on the 103B model, we see that smooth quant seems to help a bit across tasks. Here you can see we have all of our tasks, and then we have whether it's a Latin Indo-European language or anything else. You can see what I referred to before. You'll notice that just about all of the non-Latin non-Indo-European languages, you'll see their degradation is worse even when we look per task. But so yeah, so we see that smooth quant seems to either help a little bit across the board or definitely not hurt, except for MGSM. There's always exceptions to every rule. And group-wise scaling seems to really help. So if you are going to do W4 quantization, it seems like it makes much more sense to use something like GPTQ or W4 with group-wise scaling. Particularly here in the MGSM, we were able to bring the degradation from about 10% to only about 5% for the non-Latin scripts, non-Indo-European languages. Okay, and now for our LLM-as-a-Judge and our human evaluation, we have our breakdown by internal test set, the more challenging one, and by DALI. You can see that for this internal test set, as we increase the quantization, as we go down the rows, the performance drop gets a lot worse. So, we're on the order of 20 and 30% drops as judged by LLMs or reward models for French, Spanish, Japanese, and Korean. So severe drops here. For DALI, we got a little bit less signal. It appears as though that W4G is worse. I'm seeing a lot more red there. Our hypothesis as to why we are seeing more noise here is because the DALI prompts are simpler. So we thought we got more signal from the ones that are still challenging for modern LLMs, which would be the internal ones. And interestingly, for Spanish with quantization, it seems like we were actually beating our FP16 baseline. Yes, we have a question.
Hi, Kelly. So my question is that during quantization, which group of languages, perform better during quantization, and which group of languages, struggles to perform at the results by quantization?
Yes, we have this breakdown per language in the paper. I should have had a slide with this. But particularly, it seemed as though the closer the language was to English, the less it suffered, which makes sense. Those are going to be the ones that have the most amount of data. They're most related to what was the focus of the model, for better or for worse, during training, which was unfortunately English. We often, I believe, if I recall correctly, we did often see big challenges in Japanese and Korean, but all the language by language results are in the paper.
Thank you.
Yep. Yeah, and just as a side note, like all LLM and RM as a judge metrics need to really be taken with a grain of salt, because for the LLM, this was GPT-4 was used as the LLM judge. We don't necessarily know how good it is at various languages. So I would not make the conclusion that, oh, French suffers more than Korean necessarily, because it could be the case that maybe the LLM judge is just not very good at judging Korean. So we really want to look into the human eval, but LLM as a judge under some scenarios can provide some signal. It's often better than nothing, and it's certainly a lot cheaper than hiring a bunch of annotators. Did we have another question from the audience? I think I see a hand up. Maybe that was from before.
The previous
from before. Okay. All right. And then if we look at human evaluators, this one we should trust more. W4G, we can see on internal prompts, does have a lot of degradation. Interestingly, on the DALL-E prompts, we seem to see some boosts in human evaluation after quantization for Japanese. Again, it's hard to, I mean, this is a big number, hard to really say what this means, because even human eval isn't perfect. And these DALL-E prompts are easier than internal. Okay, this is actually the last slide, so we have plenty of time for questions. So the conclusion from this paper is that the ability to serve low compute models is critical for wide global adoption, but even widely used methods for quantization such as W8 lead to degradation detectable by humans for some languages, and W4 is even worse. So this work underlines the importance of considering multilinguality as a key evaluation criterion for efficient models.